When multiplying radical expressions, we will need to make use of the product rule for radicals. This rule says that if you are given the nth root of a times the nth root of b, this will equal the nth root of the product ab. Let's do some examples using this rule. In part A, we are given the square root of 5 times the square root of 7. Using the product rule for radicals, we can rewrite this problem as the square root of 5 times 7, which equals the square root of 35. In part B, we are given the square root of 11 times the square root of p. Using the product rule again, we can rewrite this problem as the square root of 11 times p, which will equal the square root of 11p. In part C, we are given the cube root of 3 times the cube root of 12. Again, we can rewrite this problem as the cube root of 3 times 12, which will equal the cube root of 36. In part D, we are given the fourth root of 8y times the fourth root of 3r squared. Again, we can rewrite this problem as the fourth root of 8y times 3r squared, which will equal the fourth root of 24y r squared. In part E, notice that the first radical has an index of 4, and the second radical has an index of 5. In order to use the product rule for radicals, both radicals must have the same index. Hence, we cannot multiply these two radicals. We also have a second rule called the quotient rule for radicals, which can help you simplify a radical expression containing a fraction. This rule states that given the nth root of a fraction, a over b, that this will equal the nth root of a over the nth root of b. Again, let's look at some examples that use this rule. In part A, we have the square root of 16 over 25. Using the quotient rule for radicals, we can rewrite this problem as the square root of 16 divided by the square root of 25. Notice we can simplify both radicals. 16 is a perfect square because it can be written as 4 times 4. So the square root of 16 is 4. 25 is also a perfect square because it can be written as 5 times 5. So the square root of 25 is 5. Therefore, our final answer is 4 over 5. In part B, we have the square root of 7 over 36. Again, we rewrite the problem using the quotient rule to give us the square root of 7 over the square root of 36. Notice this time we only simplify the denominator because 36 is a perfect square. 6 times 6 is 36. So this gives us 6 in the bottom. However, 7 is not a perfect square root, so it will remain in the radical. So our final answer is the square root of 7 over 6. In part C, we are given the cube root of negative 8 over 125. Notice that the negative sign is lined up with the fraction bar. It is best if you place the negative sign on one of your two numbers. Usually the negative sign is placed on the numerator. So using the quotient rule to rewrite this problem, we get the cube root of negative 8 over the cube root of 125. Since we are working with the cube root, we need to check if the numbers we have are perfect cubes. Luckily, negative 8 is a perfect cube because it can be written as negative 2 times negative 2 times negative 2. So the cube root of negative 8 is negative 2. 125 is also a perfect cube because it can be written as 5 times 5 times 5. So the cube root of 125 is 5. This means our final answer is negative 2 over 5. In part D, we are given the cube root of 7 over 216. Again, we rewrite the problem as the cube root of 7 over the cube root of 216. In this case, only 216 is a perfect cube. 6 times 6 times 6 is 216. So the 7 will stay in the radical. Therefore, our final answer is the cube root of 7 over 6. In part E, we have the negative cube root of m raised to the 6th power over 125. Notice this time the negative sign is on the outside of the radical, so we make sure to keep it there in our final answer. Again, we rewrite the problem as two radicals, the cube root of m raised to the 6th power over the cube root of 125. In order to simplify the numerator, we can rewrite as the cube root of m squared raised to the 3rd power and simplify the cube root with the exponent 3. This will simplify the radical to give us m squared. In the denominator, we know that the cube root of 125 is 5. Again, don't forget the negative sign that was outside of the radical. So our final answer is negative m squared over 5. When you are given a radical expression, it is important that you be able to determine whether or not the radical is simplified. There are 4 conditions you need to look for to determine if a radical is simplified. Condition 1 states that given a radical, the radicand, the number inside the radical sign, has no factor raised to a power greater than or equal to the index. Condition 2 states that the radicand has no fractions. Condition 3 indicates that no denominator should contain a radical. Condition 4 says that the exponents in the radicand and the index have a greatest common factor of 1. Let's go over a few examples to see how these conditions apply. In part A, we are given the square root of 24. Notice that we can use the product rule to rewrite this radical. The square root of 24 can be written as the square root of 4 times 6. Note that 4 is really 2 times 2, or 2 squared. That means that the power is equal to the root, which is squared also. So this radical is not simplified according to condition 1. To simplify, we simply take the square root of 2 squared, which gives us 2. The 6 inside the radical is not a perfect square, so it will not simplify, and therefore will stay inside the radical. This gives us, as a final answer, 2 times the square root of 6. In part B, we are given the square root of 108. Again, we use the product rule to rewrite this radical as the square root of 36 times 3. In this case, 36 is really 6 times 6, or 6 squared, meaning the power is again the same as the index. So we take the square root of 6 squared, which is 6. We cannot take the square root of 3, so it stays in the radical. Our final answer is 6 times the square root of 3. In part C, we have the square root of 10. In this case, if we try to rewrite the 10, the factors we come up with will not be perfect squares. Hence, we won't be able to simplify. Essentially, what this means is that this radical is already in simplified form. In part D, we are given the cube root of 16. Again, we rewrite the radical as the cube root of 8 times 2. Notice that the 8 is really 2 times 2 times 2, or 2 cubed, meaning the power is again the same as the index. So we take the cube root of 2 cubed, which is 2. We cannot take the cube root of 2, so it stays in the radical. Our final answer is 2 times the cube root of 2. In part E, we have the square root of 16m raised to the 3rd power. Again, we rewrite the radical as the square root of 16m squared times m. The 16 is really 4 times 4, or 4 squared. The m is also squared. This means we can simplify these two factors. This will give you 4 times m. Notice that there is still 1m still inside the radical. So our final answer is 4m times the square root of m. In part F, we have the square root of 200 times k raised to the 7th power times q to the 8th power. Again, we can rewrite the radical as 10 squared times 2 times k cubed raised to the 2nd power times k times q to the 4th power raised to the 2nd power. Notice there are factors that have the power 2, which is the same as the index. So we simplify these factors. This will give us 10k raised to the 3rd power times q to the 4th power times the square root of 2k. Sometimes, in order to simplify a radical, you need to rewrite the index and the power inside the radical so that you can reduce or cancel out the common factor. This will cause your radical to change to one with a smaller index. Let's look at an example. In part A, we have the 9th root of 5 raised to the 6th power. Notice that the 9 and 6 have a common factor of 3. So this radical is not simplified according to condition 2. We rewrite the index as 3 times 3, and the power inside is 3 times 2. Notice we can reduce or cancel out the common factor 3. This will give us a radical with a smaller index. Our final answer is the cube root of 25. In part B, we have the 4th root of p raised to the 2nd power. Notice that the 4 and 2 have a common factor of 2. So this radical is not simplified according to condition 2. We rewrite the index as 2 times 2 and the power inside as 2 times 1. Notice that we can reduce or cancel out the common factor 2. This will give us a radical with a smaller index. Our final answer is the square root of p. We can also make indexes larger when we are asked to multiply two radicals with different indexes. Recall that the product rule for radicals indicates that you can multiply two radicals assuming that the indexes are the same. If you notice in part C, the indexes are different, but we can rewrite the radicals to make the indexes the same. First, we take the square root of 7 and fill in the index 2 and the power 1. Next, we take the cube root of 2 and fill in the power 1. Note that the indexes 2 and 3 have a common multiple of 6, so we want to change the index on both radicals to 6. This means for the first radical, we need to multiply the index 2 times 3 as well as the power inside 1 times 3. In the second radical, we multiply the index 3 times 2 as well as the power inside 1 times 2. This will give us the 6th root of 7 raised to the third power times the 6th root of 2 raised to the second power. Now that both radicals have the same index of 6, we can use the product rule to multiply. This will give us a final answer of the 6th root of 1,372. You should look over the examples on the web page, then test your knowledge using Test Yourself.